to which point you know the topic or you know the material. So what I want to do is to give an overview of what has been done so far, what are we working on, and also what are the challenges for the future regarding ODS stills. So, I went too far. So I will start just by, well, the ODS. I just started using the ODS acronym, but you may or may not know. And ODS stands for Oxide Dispersion Strengthened. And that actually describes well, one of the main characteristics of these materials, because they do possess an nanometric dispersion of oxides, which is induced by the manufacturing process, and these small nano oxides act as sinks of dislocations and defects that may be induced during their operation, because that can happen while they are used as, for instance, in this picture that I show here. Okay, they remain as main candidates for use in advanced fusion reactors, and that answers this question I display here. Why do we study ODS stills? Well, that's it. Okay, they have remained for candidates to be in a fusion reactor. This is an image of ITER that you probably know or are familiar to it. And you see here, I am pointing at the blanket modules and the divertor. So due to the location that they are aimed to be inside the reactor, they will have to work under extreme operation conditions of both high temperature, irradiation, and a set of harsh conditions. And well, not only this. Let's see what are the requirements that we are claiming for advanced materials to be used in a fusion reactor. As I mentioned, due to their location inside the reactor, the structural materials will be exposed to a set of different loads, including mechanical loads, well, because it's a heavy instrument reactor, electromagnetic loads, thermal loads, and also a high neutron flux. All of that at the same time. So the requirements that we are claiming for the structural materials is this long list in here. So we want everything at the same time. Okay, we want good mechanical properties at high temperatures. That's a challenge. We want them to be ductile, them to have a low ductile to brittle transition temperature, that they can support the high heat fluxes at the surface that they will have to undertake, resistance to thermal shock and thermal fatigue, good thermal conductivity, and thermal expansion coefficient. I'm just reading them all to realize how demanding we are for them. Okay, it's very important that they have a low induced activation, and all these other things, resistance to radiation damage, that we were able to weld them, okay, and give them any required shape that we may need. Also corrosion resistance and the possibility to produce them at an industrial scale. Some of these requirements have been achieved in some of the materials, but some of them remain as a challenge. And for all these requirements, we are not only claiming that they are present in the materials at the same time, we also want them to be maintained during the operational life of the reactor. And well, you may agree with me, that's a lot to ask, but well, that's how we work. Yeah, we want a lot of things. We want them quickly, and we want in the long term. And I might say, well, that the materials that we are talking about today, well, they already meet some of these requirements, and we will see them over the next slides. I would like to list a few of candidate structural materials that the science community have been working already. And I'm splitting them in two groups. Okay, so the first group, of austenitic steels, titanium, nickel, niobium, molybdenum, and aluminum alloys, we may label them as previous candidates. And these other ones in the bottom, the ferritic martensitic steels and ODS steels, tungsten and vanadium alloys, and silicon-based materials, let's name them as current candidates. Regarding the previous candidates, I went fast. Sorry. Yeah, so the reasons to discard the previous candidates. Austenitic steels have been considered for structural materials for years, and they are attractive because they have good mechanical properties, they show good resistance to corrosion and good weldability, and there's a great technology maturity for producing them, and they are industrially available in different forms. There's a great operation experience with them in fission systems, but for the austenitic steels, due to their FCC structure, they show a high radiation damage, and also they show a high swelling and embrittlement due to the helium and hydrogen production in the high neutron flux. And on top of that, they are not compatible with liquid lithium and lithium lead. That is something that is going to happen in a fission reactor. So austenitic steels, they have a large application or in some other points, but not for fusion, let's say. And the problem with titanium alloys, I'm not discarding them for anything else, okay, but only for fusion applications. For titanium alloys, well, their hydrogen affinity, well, there's going to be hydrogen produced inside the reactor. So if there is affinity for hydrogen from titanium, well, that makes it almost non-usable. And it forms fragile hydrides, so it will mean a serious problem. Regarding nickel alloys, they suffer an important hardening effect under irradiation. Again, something to be avoided. And the other alloys that we mentioned, niobium, molybdenum, and aluminum, the main problem is that they are highly activated after operation. And the environment is quite something to be concerned about. Okay, when a high activation in any of the involved materials needs to be avoided. Okay, so any of these high activation elements should be either eliminated or substituted. And the current candidates that we mentioned, the elements that they mainly have are, all of them are of low activation. So that's why we mention them as current candidates, okay, because this low activation is one of the main reasons, okay, because waste with high long-term radioactivity should not be generated. And if we use this set of, let's say, elements from the periodic table that are not active in the long term, they represent a promising candidate or a promising element to have into account. Let's see some other reasons to validate these current candidates. We have the operating temperature. We know that shows the temperature range in which the performance of each of these materials will work well, let's say. Okay, so if we look at, let me show you here, we have the ferritic martensitic steels, and that can be improved by this nanometric dispersion of particles that I mentioned. We can increase the operation temperature by 100 degrees or so. And that's interesting, okay? And it means that it's one step forward to where we mainly were. And here you can see the silicon-based materials are around here, okay, well, in a very interesting range in the temperature. And on top of that are the tungsten and tungsten alloys. Okay, they can work at the highest temperature, and that's why they are used as directly plasma-facing materials inside the reactor. But there are many parts in the reactor that needs to be, specific materials need to be located at. So as this is our interesting material of interest, okay, let's focus into here, and they cover an interesting range between, well, the main one is between 300 and over 700 and up to 800. Let's see how we can improve this. Okay, this graph was produced by Stephen Finkel in the millennium, in the 2000. There have been some improvements, but not in an standardized way. I mentioned about the lower activation of these alloys, and here we can see that, well, at least the ferritic martensitic steels initially developed over the 80s, 90s. Okay, all of the ones that we are showing here are commercial alloys, commercial ferritic martensitic steels developed in the 80s and 90s. Okay, except the Manet 2 version, okay, with that we see that it contains niobium, not a high amount, but that content in niobium just makes it to be in the high level waste, and that makes it not interesting. Okay, so the most, let's say, safe in terms of activation is the Eurofer 97. So the ferritic martensitic alloys developed in Europe. 97, I think, is the year in which it was produced. So regarding the low activation, they definitely are interesting and favorable to what we want, okay, to avoid active waste in the long term. But we looked previously the operational temperature, okay, and well, we see that the operational temperature for ferritic martensitic steels is good, is interesting, but we may want it to be slightly better or even much better. Okay, so that's the next step, is to start from a ferritic martensitic steel that shows good properties and low activation, and try to improve their mechanical properties and the performance at high temperature. We can obtain that with ODS steels. Okay, and there was again a set of commercial alloys started started to be developed around in the same time as ferritic martensitic steels, around the 90s, let's say, and they were produced by different companies in Japan, in Europe, and in the US. It is MA956, 957, and PM2000. They were produced, as I say, by different companies, but well, they are not, let's say, available at an industrial scale. And well, I don't know anything regarding with companies. You may have had some experience. It's something in which you lack of information. You don't have all the data that you want to, and it's something that it's there, okay, but we don't have them, let's say, anymore, or know to apply them to get tons of any of them to use for a fusion reactor. Okay, and I would like for us to look at this graph in here. Okay, we can see that any of the ODS alloys compared to the, let's say, to a non-ODS model material, which is in here, well, all of them improve their mechanical properties respect to the non-ODS version. And in the bottom part in here, okay, the 12Y1 and the 12YWT are experimental alloys. Okay, so they are laboratory alloys, non-commercial ones. But well, we can see that well, the experimental alloy it's the same better, or at some point even better than the commercial alloys. And this is the interesting input that well, the ODS community has. Okay, we can get something that is as good as commercial, well, for whatever the reason it is, Okay, and we see that ODS steels will sound like a good option, an interesting option. It has very interesting potential applications, and yeah, we know that it's going to work, and we can say, well, okay, let's do this, let's go for it, definitely. Well, how do we manufacture them? How can we get a real ODS steel? So having this this background here, okay, that it has been demonstrated that ODS steels show some of the requirements that we were claiming at the beginning about performance at high temperature, okay, and no swelling, and some other bits that have been studied all over the years. Let's see, how can we manufacture the ODS steels? And it is, well, I'm brave enough to say that it's quite easy. Make well, easy. Let's quote it. Okay, but we can obtain all these steels by a standard powder metallurgy route, which typically includes mechanical alloying, followed by different consolidation routes that can include hot isostatic pressing, forging, spark plasma sintering, hot cross-rolling, or hot extraction, or a combination of them. And they are typically followed by a heat treatment to release any stress that could be induced by the process itself. Okay, I will show you some examples of the mainly of the situation that I have handled myself. Okay, that is the one that you can know better. So how we have prepared our own ODS steels in Madrid. We have started from a powder mixture preparation that could come either from the elemental powders that we want to have in the final composition, or from pre-alloyed powders that we have mixed with yttrium oxide. And these are the compositions that we have worked on typically at Carlos III. It's very important that we have a reference material, so a non-ODS version of the alloy, and to add other elements one by one, if possible. Okay, so we started adding just yttrium oxide particles, and after that, tungsten and titanium, because tungsten forms stable precipitates that can enhance the mechanical properties, and the presence of titanium has demonstrated that it refines the distribution of the nanoparticles and also the microstructure of the material. So as we start mixing powder, the powder is micrometric at the beginning. The surface volume ratio is very high. So we need to avoid oxidation, contamination of the powders that we are handling, okay? Except for the yttrium oxide, that is an oxide, is not going to oxidize anymore, but all the others, especially titanium, can oxidize due to the exposure to atmosphere. So we need to do all the handling under a glove chamber in an argon atmosphere. And after that, we go ahead with the mechanical alloying that can be performed in different devices, okay? Attrition milling, ball milling, or this simulator that I show here in the picture, which is actually the device type that allows to produce a semi-industrial amount of the material, up to 10, 20 kilos. And well, this is one of the handicaps that we may highlight for something to complain is that all that I am talking about is laboratory scale. And well, if we want it to be scaled to the industrial level, well, there are a bit bits to undergo. So I list the mechanical alloying parameters that we need to take into account: as the milling atmosphere, the ball to powder ratio. It will affect the energy that is involved in the process, rotation speed, milling time, and there is an optimization process that we need to individually undergo depending on the device that we have, the powder composition, the powder properties, etc. Okay, so we attempted this, we used these two pieces of equipment at Carlos III. And the first one was one planetary ball mill with only one vessel. So if you see here, it just took forever to get 80 grams of alloy powder. But well, once you know the process in the small scale, we just jumped to a more developed alloying machine that well, with 4 vessels that well, could optimize our time by 4, because in a 60 hours total time we could obtain 320 grams. It's still laboratory scale, okay, but still at that scale we can improve our bit well, quite a lot. The first step, that the first thing that we need to do is to check the powder that we have milled, okay? And not only to evaluate the size and the shape if anything goes wrong or whatever. In here we can see that we start with several nominal compositions, but well, they look what we expect. Okay, these irregular shapes, it's something that we can definitely expect. We need to check if the composition is homogeneous or not. Okay, so we perform different point scans, and we check that well, the composition of most of the grains and regarding the size or shape is the same, because well, this is an example of a failure that we had in the past. Okay, we can see that the powder was not homogeneous at all. And this was a titanium, zirconium, niobium, tantalum alloy, and we can basically identify the elements individually according to their brightness linked to the atomic number. And well, this is a total fail, okay? But our experience is, keep it into account, you probably agree with me, is mostly based on fail than on success, okay? So there was a big learning from this result that, well, made us realize how important it is to check that our powder is homogeneous. So yeah, the powder is homogeneous, and after that we measured the size of that powder, and we can see at this very first step that well, the grain size of anything having yttrium oxide or anything else could reduce the powder particle size by half. Okay, we went to a 50 microns size powder to 20 something. Okay, when we added yttrium or tungsten and titanium. And regarding the crystal structure, we obtained an alpha phase structure for the powder. Any minor crystallographic regions could not be detected in standard X-ray diffraction. After that, well, we consolidate the powder by hot isostatic pressing. We first need to can and degas the powder to avoid the presence of any porosity, and we submit it to a hot isostatic pressing at high temperature and in an argon atmosphere. And this is how the can that we use looks before and after the process. We combine the heap with a forging process, okay, which has been done more I don't know, for I don't know, for centuries in the history. Okay, but this process that is still applied, and depending on the composition of the powder, we may require higher temperatures. Okay, so yeah, here we can see that our alloy containing tungsten required the highest temperature for forging. Okay, and this is what we obtained. We obtained laboratory scale batches that we submitted to a heat treatment later to release any stress. We also attempted the hot cross rolling process, okay, in which we reach thickness reduction of 70% from the can similar what I showed before after heat, and we also subjected it to a heat treatment. Another possibility that we have is the spark plasma sintering that provides interesting results, but well, the size of the sample that we obtain, it's quite small, okay, because it's a disk of 40 millimeters and 10 to 12 millimeters height is a small disk that, well, if we're thinking about industrial production of this, well, makes it a bit difficult, but well, still is a possibility. And let's have a look at some results, okay, after of the consolidated material. The non-ODS alloy prepared under a helium atmosphere, that's important, and that gives us an idea of what is better or not. We observe the duplex microstructure, both micron and submicron side grains. We see a chromium-rich precipitates at the boundaries and within grains. With this, that they were indexed as chromium oxide or metal 23C6. And something interesting is that we observe these voids here. Okay, in this case, they were kind of large, between 5 and 25 nanometers, that within grains, and attached to these locations, and so that could be, well, at some point detrimental to the mechanical properties. And here we see the same milling atmosphere in helium, but with yttrium oxide. And here we can observe clearly this nanometric dispersion of particles that I mentioned at the beginning. And these are the important ones because they are going to act as sinks of dislocation propagation, and they are going to enhance the mechanical properties of the alloy. And here we can see that from EDS measurements that they are yttrium-rich, and we also observed a chromium-rich show around at least the larger particles. Okay. Something interesting is that in this case we observe the bubbles, or nanometric sized voids, but they are smaller in this case. They are smaller than 5 nanometers. Okay, it could be due to the presence of yttrium oxide. That is the difference between the non-ODS version, and they observed to be attached to the ODS nanoparticles or dislocations or grain boundaries. And in here, if we look at the same composition but prepared in a hydrogen atmosphere, we see that the duplex microstructure is not there anymore. Okay, we just get an uniform grain structure that provides a more homogeneous microstructure. We can observe the chromium-rich precipitates. These types of chromium-rich precipitates are present in most of the alloys that we prepared, but having no voids in the material, it's also a good property. Okay, and well, if we need to decide between milling in helium or in hydrogen atmosphere, we go for the last one. Okay, regarding the yttrium oxide nanoparticles, we can still see that the fine dispersion is present inside the grains, and some of them are attached to chromium-rich particles, as we can see here. Okay, we can see the map is the chromium-rich particle and the yttrium particle attached to it. That is frequently observed. We also did atom probe tomography in this alloy, and here we can see, well, in TM we see 2D view of the nanoparticles, but atom probe tomography allows us to see it in a 3-dimensional view. And here we can see that well, this nanometric dispersion of particles is actually homogeneously distributed, at least inside the grains. We can see here, and if we combine the results of both techniques, transmission electron microscopy and atom probe tomography, or from TM we can get well, some measurement, for instance, of the size of the nanoparticles, and in atom probe tomography we can have a measurement of the smallest nanoclusters. Okay, so those that we cannot clearly see by TM. So they're a good complement. Okay, and also, well, in atom probe tomography, except in very specific and very favorable cases, we cannot get an idea of the crystallography of the nanoparticles, or at least I couldn't in my experience. So we can combine the information that we can get from TEM by diffraction. Okay, we can identify the crystal structure of some of the nanoparticles, But from atom probe tomography, we can analyze the chemistry of each individual cluster. Okay, so we can combine information from both techniques, and what gives us the whole information about our material is to apply a multi-technique analysis. That is for sure. Not only one characterization technique are going to give us all the answers. When we add tungsten and titanium to our alloy, we obtain again an aqueous submicron grains, but the presence of tungsten and titanium gives place to different types of particles as well. And we observe chromium tungsten rich particles in here, the largest ones, chromium titanium rich, and again, the dispersion of yttrium and titanium rich nanoparticles. Most of them fall in the nanometric range, most of them less than 10 nanometers in size. And I would like to show you what we obtained by a spark plasma sintering, which you can see that the images are not as good as the previous case. Okay, but after hot isostatic pressing, we can observe aqueous grains in the non-ODS sample, and we observe some martensite labs present in the sample, because the point is that there was a huge high amount of carbon that was not intentionally included in the powder metallurgy route, but came from the liners that have to be used in the spark plasma sintering process. So carbon from those liners came into the alloy during the process, okay, because we passed a high current through the material, and it was incorporated in the alloy and formed these martensite fats. And here we can see another, well, we can see that the chromium particles are higher in number and higher in size than in the other case. And for the ODS version of it, well, it was quite of a fail, because we can see a high porosity. Some of the grains are aqueous, but most of them are elongated. Okay, so the microstructure has nothing to do with what we observed with the heat sample, in which was much more homogeneous. And regarding the yttrium-rich nanoparticles, well, they seem to be present, but well, the distribution is not as homogeneous as we could see in the previous case. And I'm going a bit, I'm going to be quickly through the mechanical characterization, because I don't want to run out of time. So if we look, let's see some snapshots of the non-ODS alloy, the one containing yttrium oxide, the one containing tungsten and titanium, and the SPS one, both versions, non-ODS and ODS, and compare them. Okay, let's put them together. So we see that the sample containing tungsten and titanium shows the best mechanical properties in the high temperature range, compared to, of course, to the non-ODS version, but also with the sample not containing tungsten and titanium. Also, if we compare the uniform elongation and total elongation, and if we compare them all together, we see that this HIP ODS2 is the one containing tungsten and titanium. If we look at the high temperature, we may set our preferred alloy as the ODS version containing tungsten and titanium, according to these results so far, and according to the microstructure and the mechanical properties observed. So we say, okay, this is our preferred one, but well, let's not forget that this material is supposed to be used inside a nuclear reactor. So how can you test that? How are you sure that we are sure about the manufacturing process and so? What we did was perform an irradiation experiment. So we subjected our sample. In this case, it was hot cross-rolled, but the microstructure was as good as the heat one. Okay, so we subjected it to a dual ion beam irradiation experiment in the Janus Saclay facility. Okay, we used iron ions up to 30 displacements per atom. and helium flux for 600 atomic parts per million, according to these extreme calculations here, and at a medium temperature of 400 degrees C. And what we could observe, these results are work in progress. We can see a comparison between the unirradiated and post-irradiated sample, and the homogeneous distribution of nanoparticles is still present. And the main difference that we can observe between them before and after irradiation is here you can see is that some of the precipitates change the shape from round to square. Okay, this is something that we are currently looking at. It may be related to the coherency between the precipitates and the matrix. And we are not sure about the mechanical implications that it may have. As I say, it's work in progress, but well, it's something that is there. We also made atom-prof tomography from the sample, and if we look at the sample before and after irradiation, they look pretty much the same. Okay, and up to this level, if we measure the cluster size, okay, we can just observe a change in a higher amount of smaller particles, which may mean that well, some of the larger precipitates may have dissolved and reprecipitate again as new and smaller ones. And in atom-prof tomography, we can also measure the distance, well, in atom-prof tomography or in TM, actually. But in this case, we measure the distance between the one precipitate and the first neighbor. And that intercluster distance was slightly closer, let's say, after irradiation. So, yeah, enhancing our statement of some large precipitates being reprecipitated after as smaller ones. And if we look at the cluster chemistry, well, we can look at the chemical composition of each individual cluster characterized here. And we can see is that, well, some of the smaller clusters just lose the titanium content. Okay, so some chemical changes may be happening, okay, or some partial dissolution of the precipitates, because even though we can see that the average values are roughly the same, if we look closely to one graph and the other, we can see that the individual content of each element in the precipitates is not the same. But then overall, we observe slight changes only, confirmed by the little microstructural evolution after irradiation. So at least up to this point, we can say that there's a tolerance of this alloy at the given irradiation conditions. And this is actually, well, we just looked at one specific irradiation condition. Okay, and well, this there is actually, as mentioned in this paper here published in 2017, the authors highlight that well, the experimental conditions used for irradiation in ODS still are highly variable and inconclusive, and together with the different compositions, the different characteristics that ODS prepared by different laboratories have, makes it very difficult to understand the irradiation effects on ODS stills, and it makes it a real challenge. And just well, to wrap up, I would like to make well, a summary so far. So well, ODS stills have remained and still remain as structural material candidates for nuclear applications. The presence of this induced dispersion of oxide nanoparticles, well, has really demonstrated a positive effect on both the mechanical properties and the microstructural stability at high temperature. And they have shown radiation resistance, at least under certain irradiation conditions. This is good so far, but there is a set of challenges to overcome for sure, and that makes it part of our future work because we are not done with ODS stills. Okay, there's a lot of work done, but it's definitely a lot of work to be done as well. Like for instance, and recalling what it was mentioned in this paper, to explore a wider range of the radiation conditions that may allow to predict the performance of these alloys in a real nuclear environment. We can explore modifications in the composition. There are some attempts in either adding zirconium, substituting titanium with zirconium, or any other combinations. Also to explore new production routes, because we have been stuck with powder metallurgy. The point is that it gives us a lot of self-confidence, okay, because it's a well-known process and we know that it works, and we're afraid to go to leave it and try some other thing, but some new production routes can be explored. The ability to produce all these stills at the industrial scale remains still as a challenge. Okay, and there's still up to tens of kilos can be produced, but what if we need tons of it? Okay, is it scalable? How we are going to do it? Is there any company interested in going for it? Still a question. That's why I set all of them as questions. And it's even ODS still is mainly focused to be used as nuclear. In the nuclear fusion reactor, there's also a possibility to be used as fuel cladding materials in fast reactors. And there's some attempts still being done in this sense. And well, these are mainly some of the questions I ask myself about the topic and how to move forward. But well, I will be pleased to answer any of the questions that you may have already, or if we can discuss or complain about the topic right now, I will be pleased to do so. I'm not sure if I just went above my time. I apologize, but I cannot finish because it's one of my favorite topics ever. So, well, thank you so much for your attention, for your time today, and yeah, let's discuss.
Thanks, Maria. It's really a great talk, and it's all in time. No worries at all.
Oh, thank you so much.
Yeah, and I think you've shown a lot of reasons to make choices, like to choose specific alloys for the fusion application, which is great. Like for me, who don't know this field much, I think it's a really good talk. And also you showed a lot of detailed characterization analysis, which is also very interesting. Thank you.
Thank you. Thank you.
So do we have any questions from our audience? Maybe I want to ask, yes, Thomas, please go first.
Oh, I'm on. Okay. Hello.
Hiya.
Yeah, thank you for the talk. Very, very nice and very good characterization work. You mentioned, I think, a low dBTT is one of the criteria for these ODS steels. So I just want to ask if these oxide particles, do they segregate the grain boundaries? Does it lower the Sharpie energy and brittle the grain boundaries, that kind of thing?
Well, the dBTT that we have observed so far is around maybe, let's say, between, depending on the sample, is between below 0 and up to 100 degrees. And up to 100 degrees, it's not good at all. Okay, our best case is below 0. That is the best that we have observed. And the oxide precipitates, they mainly distribute inside the grains, but some of them and some of the larger ones, they attach either to the chromium-rich particles, as I showed in one of the slides, but they are also found in the grain boundaries. Yes, they are, and that's probably the reason. You are definitely right, and that is some aspect to improve as well. Yeah.
Okay, cool. So it's one of the challenges, I suppose, to keep all the particles within the grain rather than allow it to segregate.
Exactly. Yes.
Okay, cool. All right, thank you very much.
Yeah. Thanks for the question. Very good one. Yeah.
Okay. Thank you.
Yeah, can I ask a question about the size distribution of your powders?
Yes.
I see that in one of the slides you should compare the fine distributions and the bigger ones by half or doubled.
Yes.
But there is a bit tail for the finer particles.
Yes. Yes, you're right.
Yeah. So for those, I also see these bigger ones in the micrographs as well. So are they a trouble at all or not really? Like,
the point is, there's a trick for that. Okay, yeah. I just showed the distribution of the powder after the milling process. So and they can also be seen in the SEM image for sure. So what we do is that there might be a risk of having too large particles together with very small ones. It may be a problem in the consolidation process. So what we do is to remove them.
Okay. Yeah.
Okay. So we just sew them with we use 100 micron filter. So anything larger than 100 micron size powder, is out of the consolidation. Yeah.
Yeah, it's great.
So you know the stuff. Yes. Absolutely.
Yeah, wonderful. And also, like you said, after radiation, there will be some spheres becoming some square-like shapes, morphologies on the 2D. And can APT see this? No, or not yet.
The point is that due to the aberrations that are present in the atom-prof tomography technique, it is really difficult to get, especially if you have round shapes and square shapes together in the same volume. It is very difficult to differentiate between them.
Yeah.
Okay, so we aimed, and when we do the atom-prof, the cluster analysis by atom-prof, we are somehow pre-assuming that they are going to be round shape, and even we approximate them to an equivalent sphere.
Yeah.
So it is really challenging to identify any squares in the atom-prof tomography characterization. And also the square precipitates that were observed by TM were the larger ones. So probably specifically the ones that we are not seeing in atom-prof.
Yeah, I see. Yes, it makes sense, because for us, I also do some coarsening studies in other completely different system. And after coarsening, it can have some slightly facets, like i.e. squares.
Yes. Yeah, well, it's by the way, it's a very interesting situation, and it's the first time that we deal with it. But it's really interesting, and we are looking very closely to it. So it's still work in progress. Yeah, that's the thing that we are currently working on.
Yeah, it's great. Thank you. Any other questions, guys? No? All right. Okay. If there's no questions, because Maria, we actually recorded this video, your talk. I will send it later for you to prove.
Okay. Fantastic. No problem.
Yeah, and also after that, like if anyone see your video later and from the audience will ask you, can email you about further.
Of course, sure. Of course. I didn't mention. I will be more than happy to if I can help or discuss, or if you have any suggestions to what I showed, I will be delighted to receive any email from you. Yes, that's why I displayed it. Sure.
That's great. Thank you for your time.
Thank you so much. No, thank you all. Thank you all the audience for your time and your attention. Again, it's been my pleasure to be here today. And well, let's keep in touch, please.
Yes. I think we'll do. Great. Thank you very much. Thank you.
Okay, thank you. Have a great day, you all.
You too.
Bye.
Bye, everyone. Bye, Maria.